So, factoring by dividing. Factoring, as I mentioned with the GCF, is actually the inverse of multiplication. It's undoing it. It says, what did it look like before I multiplied? Now, there's another thing that we often say is undoes multiplication, and that's division. And it's actually true here. The idea is that there are several equivalent statements about a polynomial. They are, some of them, the ones that are relevant here, is that x minus a is a factor of a polynomial f of x, and that is equivalent to saying that f of x is divisible by x minus a. That comes from the idea that, well, to use an example of numbers, 10 divided by 5 is equal to 2, and we can reverse that and say then that 2 times 5 is equal to 10. So the idea is that if f of x divided by some divisor gives us a quotient with no remainder, then the quotient times the divisor is equal to the original polynomial. And that gives us a way to factor the original polynomial. Now there is one other important equivalent statement here. X equals a is a zero of f of x. The reason that's important is because of something called the rational zero test. The idea is that there's got to be some way to figure out what the potential zeros of a polynomial are. Well, let's remember the form of a polynomial. A sub n, x to the n, etc., counting down until we get to a sub 0. So the idea is that all of the coefficients are labeled by the variable a, but subscripted by by the degree of the term that they are attached to. The idea is then that all potential rational zeros are of the form some factor of a sub 0 over some factor of a sub n. That's an interesting kind of thing. Where would they even have come up with something like that? That'll be easier to explain after the fact when we see the results of an example. So let me first talk about how, and then we'll come back later on and talk about why. So we're going to use a polynomial here as an example that we would not otherwise be able to factor by grouping. It just won't work. We'll see that. So the polynomial is 6x cubed minus 19x squared plus 12x, plus 16x, get my problems mixed up, plus 16x minus 4. Now, first of all, you're not going to be able to group this. I mean, you can separate it into groups, but when we take out the common factor of each group, it's not going to give us what we need. So the common factor here could be x squared, but since we're not taking out anything from the coefficients, since they have nothing in common, that means the coefficients don't change. So it's still 6 and negative 19. There is absolutely nothing we're going to be able to do here that's going to result in a 6x and a minus 19. That's just impossible. So, I mean, there is still something you could take out, yeah, but it's not going to actually accomplish anything. So since these two things don't match, the grouping method just kind of sputters out and dies here. So how on earth are we supposed to factor this? Well, perhaps we can find something that it divides by perfectly. So let's take a look at this rational zero test. First of all, this here is our a sub 0. And this here is our a sub n. So it might help to start by listing out the factors of them. The factors of 6 are 1, 2, 3, and 6. And the factors of 4 are 1, 2, and 4. Now, when we say some factor of a sub 0 over some factor of a sub n, what it means is that any rational zero would have to be one of these numbers in the top of the fraction and one of those numbers in the bottom. Sounds awful. Not nearly as bad as you might think. What I'm going to do is just go through them one at a time. I'm going to take each factor from a sub 0 in the top and put it over each of these in turn. So what we could have is 1 over 1. And by the way, these factors can be either positive or negative. That's why I didn't include the negative up there, because we don't need to worry about positives and negatives here. That'll be covered by the rational zero test itself. 1 over 2. 1 over 3. And 1 over 6. I'm then going to repeat it with the 2. 2 over 1, 2 over 2, 2 over 3. So 2 over 1, 2 over 2, 2 over 3, and 2 over 6. And once more with the 4. 4 over 1, 4 over 2, etc. Now, this looks awful. There are 12 different combinations of numbers, and then each of those 12 could be either positive or negative. That's 24 possible rational zeros. Now, this being a third-degree polynomial, it can actually only have at most 3. It may not even have that many if some of the roots are actually complex. But if there are going to be any rational zeros, they're going to be one of these. So, 24 possibilities? Well, actually, it's not as bad as it might sound. Some of these are doubled up. Like, for example, 2 over 2 is actually the same thing as 1 over 1. They're both equal to 1. So this is kind of duplicating what's already there. So why would we bother? So that's 2 possibilities gone, but while we're at it, 2/6 is actually the same as 1/3. So that's covered. Actually, for that matter, while we're at it, 4 over 2 is the same as 2 over 1, and 4 over 6 is the same as 2 over 3. So 8 possibilities kind of already covered because they're duplicated. Alright, so that still leaves us with quite a few. It leaves us with 1, 1/2, 1/3, 1/6. It leaves us with 2 and 2/3. And it leaves us with 4 and 4/3. Alright, well, that's still an awful lot of possibilities, but might I suggest there's a few of them that are distinctly preferable? Like, how about the integers? Now remember where we're going with this. We're going towards division. I would think it would be much easier to do the division if we had a factor that involved a whole number rather than a fraction. While you certainly could do it with the fractions, they're going to be much uglier to deal with. I'd rather start with the easy things. You always start with the easiest possibilities. Now, even if some of the fractions do actually work, it's actually not going to matter. As soon as we find one thing that does work, so as long as one of these does work, once we do the division and factor out a factor of x, we're going to be down to a degree 2, just like we saw with the GCF. So every time we factor, we reduce the degree of the polynomial. As soon as we get that down to degree 2, we should be good to go. So really, we only need to find enough things to divide it by to get it down to a manageable degree. So these are the things to pick. All right, now, long division is, as the name implies, long. It always works. Whether there's a remainder or not, you can always go through the long division algorithm all the way through to the end. But under certain circumstances, there's a shortcut, a faster way of dividing called synthetic division. So I'm going to just list out our possibilities here. X equals 1, x equals negative 1, x equals 2, x equals negative 2, x equals 4, x equals negative 4. These were our integer possibilities. The thing is, though, is if I'm saying this is potentially a 0, that means that by our equivalent statements from before, that our divisor would be x minus 1. Well, that's perfect because it's exactly in the format that we need for synthetic division. It's a degree 1 factor with a lead coefficient of 1. That's exactly what synthetic division needs. So, for synthetic division, and there's different ways to set up this bracket, but we're going to take the value of a and write it out to the side there. And we're going to take the coefficients of the polynomial and list them along the top here. And then it's a very simple pattern of very simple arithmetic. We're going to kind of zigzag our way down, filling in certain points along this as we go. And the rule is that anytime we are going vertically, we're going to add, and anytime we go diagonally, we're going to multiply by this number. So, as always happens with synthetic division, the first number goes straight down. There's nothing beneath it to add. And then from there, we go diagonal. And whenever we go diagonal, we multiply by, in this case, 1. So 6 times 1 is 6. Now we're going to go vertical. Negative 19 plus 6 is negative 13. Negative 13 times 1 is negative 13. 16 plus negative 13 is positive 3. And positive 3 times 1 is positive 3. And lastly, negative 4 plus 3 is negative 1. Now, the idea of synthetic division is that these are now the coefficients of the quotient, and this is the remainder. So what we're saying then is that if we took 6x cubed minus 19x squared plus 16x minus 4 and divided it by x minus 1, we would get 6, excuse me, I don't need the parentheses there, 6x squared minus 13x plus 3 plus negative 1 over x minus 1. This is kind of screwing the whole thing up. It's ruining the divisibility. To be truly divisible, you need to have a remainder of 0. So what that means is that this didn't work. That means positive 1 is not one of our rational zeros. Okay, no big deal. We have others to try. Now, I knew that wasn't going to work because, of course, I know how the problem's going to turn out. But I did want you to see what would happen if you try one and it doesn't work. I'm going to skip ahead then You can do these in any order you want. It doesn't really matter. It kind of makes sense to go in order because you don't know which one might work and which one might not. But I'm going to skip us ahead to x equals 2. And say, well, let's divide it by x minus 2. Well, the coefficients of the polynomial are the same. All that's changed is the value that we're writing outside. And therefore, what's going to fill in as we go? Alright, so, like before, the 6 comes straight down. Then we go diagonal, so now we're going to multiply 6 times 2. We go vertical, negative 19 plus 12 is negative 7. Diagonal, negative 7 times 2 is negative 14. 16 and negative 14 is positive 2. Positive 2 times positive 2 is 4. And negative 4 plus 4 is 0. Perfect. It's exactly what we need. So what we've got then is that 6x cubed minus 19x squared plus 16x minus 4 divided by x minus 2 is equal to 6x squared minus 7x plus 2. And therefore, by the reversing of this divisibility statement, we can say then that this polynomial, 6x cubed minus 19x squared plus 16x minus 4, factors as x minus 2 times 6x squared minus 7x plus 2. And we have successfully factored at least one round of factoring. We've now factored this partially, and the remaining bit of it is degree 2, meaning that we can use a quadratic factoring method, such as the AC method, since it has a Lie coefficient, to take it the rest of the way through. Excuse me. Now, as it turns out, and I'm going to leave that part off here because the point of this is the synthetic division, using division to factor a polynomial. Excuse me. That's not right. That's right. This would then factor the rest of the way as 2x minus 1 and 3x minus 2. Which, by the way, does fit the other rational zeros, and also helps us explain why the rational zero test works the way it does. Let's take a gander at that. Remember, the list of rational zeros was plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 2, plus or minus 2/3, plus or minus 4, plus or minus 4/3. And all of those came from the idea of some factor of the constant term, a sub 0, over some factor of the Lie coefficient, a sub n. Well, why is it that it has to be like that? And how does it actually work? Well, when you think about it, the Lie coefficient, 6, comes from the product of all of the x terms, which means it comes from the product of the coefficients of those x terms. The constant term then comes from the product of the constant terms. The other two come from mixing and matching different combinations of x terms and constant terms, but these two are the purest ones because this comes from only the x terms, and this one comes from only the constant terms. Now, check this out. Just as a little quick thing here, 2x minus 1, if I were to set that equal to 0, just bear with me, wouldn't I solve this by adding 1 and then dividing by 2? And there is x equals 1/2. This one would work in very much the same way. I'd have to add 2 and then divide by 3. And there I get 2/3. The idea here is that every one of these values comes from adding this to the other side and then dividing by that. So it's going to have a factor of the constant in the numerator and a factor of the lead coefficient in the denominator. These account for all the different ways that 6 could be broken up among these three terms in these three factors. I could have a 1x, a 1x, and a 6x. Or, as I have here, a 1x, a 2x, and a 3x. There's all different combinations of things that could happen there. And same thing with the constants. I could have a 1, and a 4, in different combinations that give me the negative. So the point is that all of these constant terms, which are going to end up in the numerators, have to come from a factor of this. And all of these coefficients here, which are going to end up in the denominator, have to come from a factor of that. Every rational zero fits that. Of course, that means we could have done the division using these two possible rational zeros, but it would get very ugly to work those fractions through the synthetic division. It's much cleaner to find something that works until it reduces the degree of the remainder, of the quotient into something that's more workable. So that's how we can use division to factor a polynomial. And one of the nice things is if you happen to be dealing with a rational expression, then you're actually already being told what the divisor is, and all you have to do is actually divide it. So that saves you a whole bunch of time. You don't need the rational zero test. You don't need you don't need to pick one of the rational zeros to use. You're already told what to divide by, and hopefully it'll actually work. In a rational function, it very often will. So that's the good news. But yeah, that's using division to factor a polynomial.